Okay, maximum material condition modifiers for straightness. Okay, MMC modifier indicates specified tolerance value applies when the feature's at maximum material condition size, so the biggest of the tolerance. Additional tolerance is permitted if the feature departs from MMC. An LMC modifier indicates specified tolerance value applies when the feature is at least material condition size. An additional tolerance is permitted if a feature departs from LMC. So you get a little bit of bonus on the straightness tolerance if one of those modifiers are called and it's not right at that limit. Virtual condition of a shaft. The virtual condition boundary created when tolerance with MMC and LMC modifier is applied to a external feature of size such as a shaft. Straightness applied MMC on the external cylinder or shaft. The virtual condition is the shaft maximum material condition size plus the straightness tolerance, and additional tolerance permitted when the feature departs from MMC. Straightness applied LMC on the external cylinder, and virtual condition of the shaft is LMC size minus the straightness tolerance. And additional tolerance is permitted when the feature size departs from LMC. Additional tolerance, or what the machinists like to call bonus. They like that word. It's not always bonuses and money, but anyway, additional allowable straightness tolerance resulted from departure from specified MMC or LMC. So the allowable tolerance is specified tolerance plus additional tolerance. The additional tolerance is the size departure from a specific material condition. Okay, so say your tolerance is plus or minus 10 thousandths on the diameter or something, and the tolerance is called at MMC, and it varies 5 thousandths. You get to add that bonus to, say, the straightness tolerance. Compliance with a virtual condition always results in the feature-derived median line staying within the allowable tolerances. Okay, the straightness of a derived median line of a hole. The feature control frame applied differently in models and orthographic views, and the cylindrical tolerance zones extends full length of the hole. So as you see in the model, it's most commonly applied with a leader line, but in an orthographic view, they prefer that it's attached to a linear or a dimension line that is going through profile. Okay, virtual condition of a hole. The virtual condition boundary created when a tolerance with MMC or LMC modifier applied to an internal feature of size, such as a hole. Straightness applied MMC to an internal cylinder or a hole. The virtual condition is the hole at maximum material condition size minus the straightness tolerance. Additional tolerance is permitted when the feature size departs from MMC. Straightness applied at LMC on an internal cylinder. This is a virtual condition is the shaft LMC size plus the straightness tolerance. And additional tolerance permitted when feature size departs from LMC. Verification of derived median line straightness. Coordinate measurement machines are great because this is a projected datum. Freestanding inspection, functional gauges that verify compliance with virtual condition. So those are functional gauges, something you'd actually physically slide onto the part. It's typically a no-go situation. The cost of gauges are recovered as the part quantity increases. It's a fast way to inspect things. And gauge designs are covered in ASME Y14.43. So if you haven't had enough of Y14.5, you could read Y14.43 when you get spare time when you're trying to cure your insomnia. Okay, and computer-assisted methods are possible for more reliable results. I saw a roundness machine that would help calculate those things, made by Metatoyo, and kind of a specific thing. It helped model where these virtual center lines, straight median lines were. Okay, overall length tolerance. Both shown in one feature control frame with 2 segments. And overall straightness tolerance is usually required when unit length tolerance is applied. So here we've got a distance, it's got to be straight within 2 thousandths per every inch of length. And overall tolerance controls the unit lengths of tolerance accumulation. And the unit length tolerance avoids small overall tolerances, which reduces cost. And overall straightness tolerance is larger. So you're typically going to have your overall tolerance larger. It's the one showing on the top in the example on the left. And a unit length distance may be any value. So it could be per inch, per foot, per whatever increment that you feel is important. That comes into play with much longer parts. Okay, verification of unit length tolerance. Functional gauge diameter equal to the virtual condition across the unit of length. So they got an example of a gauge that's at the tolerance size and width, and it's got to slide all the way down the part. The gauge length is equal to the specified dimension shown in the feature control frame. Straightness of a derived median line between flat surfaces. This is not covered by a national standard. Straightness tolerance applied to a regular feature of size containing parallel straight line elements. And each derived median line straight within a given tolerance value in the direction of a straight surface elements. MMC modifier if the same precautions are taken. You kind of typically don't use this control because there's other controls you can use, like parallelism of surfaces, but I guess they're saying in theory you can control it, but it's not specifically addressed by the national standard. Okay, verification of median line straightness. Functional gauge, if it's not adequate, with RFS straightness tolerance, regardless of feature size. Individual readings are taken at both sides of the part. Derived median line variation is then calculated, and a functional gauge to inspect MMC straightness tolerance. Okay, flatness tolerance. Specified allowable variation of form from a flat surface and derived median plate on a parallel flat surface. So this last example of doing straightness on a flat plate, kind of silly because this is how you do it with flatness instead. Only needed if a surface form needs a greater level of control than required by the size limits. No material condition modifier is applicable when applied to a surface. RFS default when applied to a regular feature of size. And MMC or LMC modifier shown when applied to a regular feature of size, and no datum reference. Okay, flatness applied to a surface in a model. Okay, flatness feature control frame includes flatness tolerance symbol and tolerance value. As shown on the left, it's pointing at the surface. Leader and feature control frame on the same annotation plane. but the associated dimension for the thickness doesn't have to be on the same plane. And leader and feature control frame on the same annotation plane. And annotation plane perpendicular to the surface achieves the greatest clarity. Oh, and attach the leader with terminating with a dot on the surface that you're denoting. I skipped that one, sorry about that. And flatness applied to a surface in orthogonal views or orthographic views is a little bit different. Okay, the same feature control frame format as in a model, but in a view where the surface appears as an edge. And it can be attached to an extension line or a leader line terminated in an arrowhead. And a leader line terminating with a dot if on the surface rather than the edge of a view, but typically you're trying to avoid that with this. Okay, flatness tolerance zone on a surface. It's bounded by two parallel planes extending in all directions. No fixed orientation and no additional tolerance based off feature of size if at RFS. A flatness applied to surface with no applicable size tolerance. No perfect form boundary to restrict form variations if no size tolerance. Inclined and skewed surfaces, flatness tolerance, feature control frames applied to specify the allowable amount of surface variation. And the feature control frame and leader on the same annotated parallel plane to one of the principal model planes and perpendicular to the tolerance surface. A verification of surface flatness. There's a couple methods, but you typically use a dial indicator or CMM. And the part rests on an accurate surface like a surface plate. And you can adjust the part orientation to minimize indicator movement. And other methods like dial indicator probe or automated process. The one I've seen most typically used is the one in the lower version. I haven't seen a whole lot of shops that are going to have a granite surface plate with a hole drill in it, and then they're going to want you to slide a part across it. If you're concerned about flatness, just that excess of movement across the surface plate is going to warp and wear down the surface plate eventually. So typically you support it by 3 points. A lot of places will use, I guess you could use machinist jacks, but you typically could use cones or things that are on points. So your 3 points make a plane. You level it out so that above each of those points are level to your table. Doesn't mean the entire surface of the bottom is of the part. And then you run your indicator across and verify that there's no movement on the needle or very little movement in the direction of the flatness, surface flatness requirement. And overall, in unit area flatness tolerance. Both are shown in one feature control frame with 2 segments, similar to straightness per unit of length. Overall flatness is required when the unit area tolerance is applied. Overall tolerance extends across the entire surface and controls the unit area tolerance accumulation. And unit area tolerance avoids small overall tolerance and reduces cost. Overall flatness tolerance is larger. And a thickness tolerance creates perfect form boundary that also affects allowable form variation. Flatness tolerance applied to a derived median plane. A flatness tolerance is applied to a regular feature of size defined by parallel flat surfaces. And it's not restricted by the limits of size when specified on feature of size. And rule number 1 does not apply to a tolerance feature of size. Feature control frame is adjacent to the size dimension or attached to the dimension line, and derived median plane variations are a result of surface variations. And the magnitude of the surface variations may not be equal to the magnitude of the derived median line variation. A verification of derived median plane flatness regardless of feature size. So the flatness tolerance applied to regular feature of size is assumed to apply at regular feature size, or RFS, unless otherwise shown. Opposed point measurements may be derived at the median plane location calculated at RFS. A verification of derived median plane flatness at maximum material condition. The flatness tolerance with MMC modifier creates derived median plane tolerance zone, and the virtual condition boundary extending across an entire feature of size. The zone width permitted to increase as feature size departs from maximum material condition. A functional gauge must simulate a virtual condition, and additional tolerance is automatically accommodated. So you actually have a physical gauge this could slide into, and it's got the gauge is calculated to have your tolerance for flatness, and you're simulating the tolerance at the center with your gauge sliding in and out and measuring the variance of those surfaces. Okay, circularity tolerance specifies acceptable circular surface element variation relative to a perfect circle and creates a boundary of 2 concentric circles. Establishes allowable variation of each individual circular element on any feature with circular cross-section. And cylinders, cones, and spheres are included. Circular cross-section exists where all points are equidistant from the axis or center point, and sometimes incorrectly referred to as roundness tolerances. Circularity tolerance is applied to a cylindrical surface. It only controls surface form. The features control frame has geometric characteristics symbol and the tolerance zone value. Never diameter symbol, MMC or LMC. Circularity tolerance is always applied to the surface, and a leader terminates with a dot in the model and an arrowhead on the orthogonal view, and boundaries are 2 concentric circles. Cylindricity establishes from size tolerance. So the cylinder diameter dimensions establishes maximum material condition, perfect form boundary. And the perfect circular boundary of each cross-section at MMC. And the circularity variation permitted by departure from maximum material condition. And this size tolerance limits the maximum circularity variations. Size variations are not required to be centered on a perfect maximum material condition boundary. Okay, circularity tolerance and size tolerance. Circularity tolerances are applied when variations are smaller than those permitted by the size tolerance. And size of one boundary established using the produced feature at each cross-section. And circularity tolerance value at the radial distance between outer and inner circles.